Hello, everyone, and welcome to part one of our lecture on Chapter 10 Analyzing Quantitative Data. So, Chapter 10 is all about figuring out how you can conduct a data analysis within a quantitative study. So, remembering that a quantitative study is primarily the study that works with numbers, looking at going into a study with a pre-proposed plan of exactly what you're going to do in the study, what populations you're going to be working with, having a solid hypothesis that you're going to be trying to look for support in either in favor of or against. And it really goes in with this mindset of, okay, I know exactly what I'm going to be studying. So this analyzation of data is a little bit more predetermined in a quantitative study, which means that we have a lot of content to cover, unfortunately. So let's get started and just sort of set the groundwork. When you are analyzing quantitative data, one of the things that pops up most frequently is the word statistics, which I know we're all in psychology, and statistics can sometimes be a pretty ugly word in psychology, but it is part of research within psychology because statistics is a branch of mathematics that uses mathematical logic to interpret phenomena and to draw conclusions from any amount of accumulated data. So, statistics is what we use to understand the research that we do when we're conducting a quantitative study. Statistics is what gives us the framework for being able to interpret our raw data and to draw conclusions from it. And really, statistics establishes relationships between and among variables and can even attempt to predict future behaviors in relationships. This is really where we get the conclusions that we draw about the work that we do in research, is from the statistical output. So even though statistics can sometimes be a little bit of an unhappy word for a lot of people in research, it's actually incredibly important. So there are different types of statistics that you run in a quantitative studies, and one of those is univariate analysis. And a univariate analysis is an analysis of only one variable, where you are doing a deep dive into understanding all that you can about one single variable. Oftentimes, univariate analysis is also called a descriptive analysis because they're very related, and that a descriptive analysis allows researchers to sketch the details of variables and gain familiarity with a sample that they're researching. So, descriptive statistics give us an idea of the descriptive characteristics of our variables. So, a good example of this is like trying to get an idea of like what's the high, what's the low, what's the average, what's the mean, what's the median of each variable in our data set. So, descriptive analysis is almost like a subfield of univariate analysis, where univariate analysis is looking at, all right, I want to just understand one variable in depth. And we use descriptive analysis almost as like a first impression of that variable. So, giving us the description of that variable that we can use to then sort of inform how we want to go further. So, what was the range on this on scores for this variable? What was the highest score possible? What was the lowest score possible? Where did the majority of people fall? What's the standard deviation on this? And we're going to talk about these terms as we go through this chapter, but that's an example of descriptive statistics. We also have what's called inferential analysis or statistics or inferential statistics. And these provide a deeper understanding of the variables that are in our study because inferential statistics draw conclusions about our population from our sample at hand. So we use inferential analysis to say, okay, based on the findings of my study, what can I say is a meaningful sort of conclusion or meaningful inference that I can make about the population as a whole based on the results that I found for my sample. And specifically, inferential analysis is a type of analysis that goes beyond the description of the data available and attempts to draw relationships or associations between variables. It's really trying to bring in more of those variables to make sense of what's going on and why we see things the way that we do. But we can also say that once a relationship is detected between variables, inferential statistics attempt to predict the possibility of applying the same relationship to the entire population of the study. So when we find something, when we establish a pattern or a relationship in our variables through inferential statistics, we are going to then start looking for that in other areas of our study through inferential analysis. We also sometimes use inferential statistics, or they operate more or less by trying to calculate the random error that occurs during data collection and analysis. So, in order for us to understand inferential statistics, we really have to evaluate the random error in our study. So, random error is associated with the type of common mistakes or errors that happen by chance when we're engaging in data collection, or when we're entering data into a spreadsheet, or we're typing in an incorrect number in our analysis program. So we're conducting an analysis incorrectly. That's random error. It is this type of error that we don't suspect, that just happens pretty infrequently and just is common mistakes or errors that everyone is bound to make. That's random error. But there's also another type of error that comes into play that's called sampling error. And sampling error is specifically a random error that occurs during the process of data collection. So, a good example of this is like random error is incorrectly typing a number wrong in our data sheet, or just like not moving all the data for one participant into our final spreadsheet. Sampling error, on the other hand, could be incorrectly coding an entire variable in our data set. That's a sampling error because it is an error that occurs during data collection that affects a much larger group of our sample. And inferential statistics only investigates the sampling error that can happen randomly. It's unable to identify a systematic sampling error. So when we use inferential statistics, we're really only focusing on the random errors. So whether that is true random error or random sampling error. So keep that in mind because it is helpful in us in understanding our quantitative studies, but it isn't perfect. And overall, univariate analysis is the first step that researchers take to familiarize themselves with the population sample in their study. We use univariate analysis as our first step in understanding all of the data that we have collected in our study to get a better idea of who's in our study, what variables do we have, and what do these variables look like so that we can draw meaningful conclusions moving forward on what we want to do next. So there are various ways that you can almost sort of depict univariate analysis information. And one of the primary ways that we sort of graphically display univariate analysis is through a frequency distribution. And constructing a frequency distribution with data is a pretty simple procedure that illustrates the key characteristic of participants in a sample. So a good example of this is that when we are conducting a study, we might have a frequency distribution that says how many people answered this question. Like maybe we have a question that has 4 different answer options. A frequency distribution is just going to tell us how many people picked option 1, how many people picked option 2, how many people picked option 3, and how many picked option 4. That's a frequency distribution. How many count people selected each answer option? And that's a good example of what we call an absolute frequency, which reflects the number of times an event or an instance has been repeated or selected. We can also use frequency distributions by assigning percentages to categories. So maybe our study is pretty big and saying like, oh, 20 people selected option 1, 30 picked option 2, 60 picked option 3, and 10 picked option 4. You're asking, with that absolute frequency, you're asking your readers to do a lot of work and saying like, okay, now I need to add all of these together and figure out like, is that meaningful? Is 10 people who picked option 4 meaningful or not? So sometimes with a frequency distribution, we'll assign a percentage to each category and say, okay, you had 30% of people who picked option 1, 35% who picked option 2, 60% who picked option 3, and so on and so forth. And those percentages are capable of zooming out from our raw numbers because it compares our raw numbers to our entire sampling population, which can be better for our readers in trying to understand what the meaning of our univariate univariate analyses are. We can also use this feature called cumulative percent, which is another descriptive measure of frequency that shows the collective percentage of categories together. So cumulative percent would say, okay, if we have 20% people who picked option A and we had 30% who picked option B, cumulatively, by the time we account for the people who answered both A and B, the cumulative percentage would be the sum of those. So 20 plus 30, we would say 50% of people have selected options A or B. And then you move into the next section and say, okay, this is how much it is until you get to the end. So this cumulative percent is something that can be helpful in better understanding our descriptive analyses, but it also is sensitive to the order of organization. So as you noted, I went in order from option 1, 2, 3, and 4 in our question, our hypothetical question that we're talking about. And that's true for any time that we use a cumulative percentage. You're always building on whatever that top percentage is and just adding to it. So you really have to organize your data in a way that's meaningful and that makes sense for your readers. So when you're doing univariate analysis, and really when we're doing any quantitative analysis, one of the first things that we use to describe our data is called a measure of central tendency. So a measure of central tendency is used to summarize an entire variable or category into a single value that is numerically representative of that variable. So when we're using a measure of central tendency, we're trying to say, okay, we have this really complex variable and we want to find a way to describe it using just one thing, one number or one word that says this is that thing. And there are actually 3 common and most utilized, actually, they're really the only measures of central tendency, and they probably are familiar to you because they're mean, median, and mode. So let's go into a little bit more detail on what each of these mean. So the first of those is the mean, which, as you might remember from our early mathematics days, is the mathematical average of a set of numbers. So if we are to calculate the mean for a sample or for a variable, we are going to take all numbers in a variable category, add them together, and then divide them by the number of people who answered that variable. So our n, the number of participants who answered that variable. And that is going to give us the total number of entries in that data set that says, okay, of all of the answer options, combine them together, divide them by the total number of people in the data set, and this is going to give me a mathematical average. And the mean is particularly useful if we're comparing 2 or more groups to one another, because you can draw meaningful conclusions across the groups if they're all using the same capacity for measuring this measure of central tendency, which is the mean. It's a statistical approach to it. The mean also is really useful in the way that it takes into account every single point in the variable, and it's particularly sensitive to outliers. So we say that a mean is helpful in that it incorporates every single variable in a data set. you cannot calculate a mean for a data set without accounting for every single variable in that category. But because we're accounting for all of those variables, that means outliers can influence the way that our mean is represented. So an outlier is a data point that is much higher or much lower than the majority of other points. If you have an outlier, so something that is either much higher than the rest or much lower than the rest, it is going to pull your mean in that direction. So an outlier is almost like a magnet that pulls the mean towards it. So the mean can be helpful in that it accounts for every single point in a variable, but it also has to be used with caution because if you have a data set that has a lot of outliers, then the mean probably isn't the best measure of central tendency. And that's why we have other options, one of those being the median. And the median represents the center point in a data set of numbers after those numbers have been arranged in either ascending or descending order. So basically what you're going to do is you're going to say, all right, I have this variable. I am going to put every single answer option that was submitted by participants in order from biggest to smallest or smallest to biggest. And then from there, I'm going to work my way in from the ends and find the exact middle variable or the exact middle value that was listed for that data. And that is our median. And the median is useful in statistics because it gives an understanding about the distribution of a variable. It tells us, okay, what is sort of like the general spread of the variable, and then where does this fall in terms of what's the actual middle point of it. But we also have our mode. And our mode is used or is referred to as the most frequently used number in a data set, which is the number that most commonly encountered in a specific set of numbers. So if you have a variable, say age, your mode is the most frequently selected age for your participants. And the mode is really nice in that it can provide additional information that can potentially clarify any misleading information that may come from the mean or the median. So, where a median can be influenced a little bit by outliers, mode tends not to be influenced because it's truly only looking at what is the most selected option. And that is our mode. Whereas the mean is definitely influenced by outliers, and a median can be, not as greatly, but it still can be. And that's why we sometimes use mode. And it's interesting when we're talking about mode because modes can be multiple. So sometimes when we're talking about a variable, it may only have one mode or it may have multiple modes. So in this image that you'll see on the top, this far left image is what we call a unimodal model. And this occurs when your dataset only has one most frequently occurring score. There's one peak in your distribution of answers. But that isn't always likely in psychological research or even in social sciences research. You might have a data set that's bimodal or one that has two modes or two peaks, as you see here in this second image. So in a bimodal model, you see two most frequently assigned scores or two most frequently assigned levels of our variable. But we can also just have a multimodal model where we're seeing three or more most frequently occurring scores, and maybe that looks something like this far right image. Typically, if you have a data set that looks a lot like this far right one, then maybe your mode isn't the best measure of central tendency. So that is where we're going to wrap up part 1 of our lecture on chapter 10. Join me for the second part of our lecture where we are going to continue discussing how we do analysis in quantitative studies. I will see you all in the next lecture.